Well, thank you to the organizers, the famous four, for having us here and enabling me to share some of our work on functional digital twinning with the CircAdapt framework, which you have heard about several times already. Well, to start, I want to say I'm not going to explain what digital twins are. You all know that. But CircAdapt, the framework, really builds on quite a history, more than 30 years of academic research in a life sciences institute, a physiology department, and a clinical cardiology. And there are several modules that have been developed and validated over time, but it's a closed loop system, and the most important characteristics, on our view, are those ones, and that is it's a reduced order model, and it's really focusing on pump function mechanics at a rather coarse level. So no 3D anatomical modeling here. Of course, that makes it very fast, and currently this is re-implemented entirely in a new framework by our postdoc, Nick van Osta. He's also present here, and I recommend you to visit his poster later today if you want to get your hands on the framework, which is openly distributed. How does that look like? Well, this is a GIF of the user interface that we built for teaching cardiovascular physiology and pathophysiology to medical students and also engineers. You can download it for free. Give it a try. It's a lot of fun. You can create your own virtual patients and learn about pressures, flow velocities across valves, and also strain patterns, not shown here. This is a quick simulation of a leaky mitral valve. And the most important thing for teaching physiology is that you can couple and uncouple the homeostatic control to that failing pump. And that is really important for teaching physiology. And then you realize that much of the phenotype a clinician is looking at is actually the regulatory actions of the system, the autonomic nervous system. Anyway, so over the years, we applied this framework to several fields of cardiology, different pathologies, comorbidities, and well, here are a few. And in this presentation, I would really like to focus on two applications where we did actually generate personalized models, so digital twins, given mostly echocardiographic information available from clinic. And that's pacing in the synchronous heart failure patients, cardiac resynchronization therapy, and also ARVC patients, inherited cardiomyopathies. To begin with, the CRT patients. So here really the question is, can we use echo data to better actually quantify the non-electrical substrates of disease? Because all those patients have heart failure, they do have their ECG problems. That is well established, that's in the guidelines. You need a wide QRS complex, but still many people do not respond as you would expect. And the hypothesis here is that is due to non-electrical substrates, scarring, loss of contractility, and so on. Well, there's a whole community investigating that using echo, mostly strain, but those signals are really hard to interpret, as you probably know. So what we did is we took, and there are many forward modeling studies that preceded this study, but I do not have the time to mention all of them. So we have 45 CRT candidates, heart failure patients, wide QRS. They do have a clinical guideline indication for implanting a CRT device. And the normal, regular clinical follow-up is that based on an echo, an ECG, ejection fraction, QRS complex, and morphology, a CRT is decided to be implanted. And then after 6 months, they look at the reverse remodeling, and hopefully the heart has become smaller and pump function improved. And of course, the symptoms of the patients. So what we propose here is that on top of that, while those are selected based on the conventional guideline criteria, we actually use strain imaging, so 18 segmental strain patterns with all their disadvantages, but also huge advantages. There is a lot of diagnostic information contained in there, and we try to fit our model to that by mostly parameterizing contractility, so the active and the passive material properties, basically. And then in these digital twins, we can apply a sort of pacing, which we assume to be the case in those patients, and see if the response in the virtual patient actually somehow correlates to the reverse remodeling after 6 months of therapy. If that's true, of course, that's quite nice, because then you can also do more in-depth phenotyping, because you did actually estimate active and passive tissue properties and also timing. But timing you would get from an ECG anyway. So this is the information that we have available clinically. So that's what we want to fit with this approach. And of course, we have done we spent quite some time to reduce our model complexity, because CircAdapt with 18 segments does contain about 300 parameters, and by no way you can actually estimate that from this limited amount of information. So we use a global sensitivity analysis. We already take out many parameters that do not have an effect on regional strain patterns or volumes. And then we go into an iterative loop with fitting on 13 patients we used for that, which are covering quite a wide range of pathology, of heart failure. And then we look at how reproducible are our estimations, and if not, we reduce model complexity to a certain reproducible estimation of these parameters. If it's not reproducible, it's not a consistent estimation, then we use these techniques with diaphony ranking to get rid of more parameters that we are not able to reliably estimate. And in the end, we end up with a final subset, and I'll show you how that will look like. So here we plotted actually the reproducibility as a function of model complexity, and of course everyone expects that the line will go up, and that's also the case. But we needed a certain degree of reproducibility to actually have confidence in our final estimations. But at the same time, we're also looking at quality of fit, of course. And that's what you lose, certainly when you go to too low numbers. You cannot fit the complex patterns anymore. So we're trying to strike a balance here and select something that we could call a good compromise. And that leads to 75 parameters on an 18-segment LV model. So what is that? That actually contains the suspected parameters, actually, that we, I think, already knew based on our forward modeling approaches. But it's good to have this confirmed numerically, of course. This is an example. So we have a real patient data set here. I don't show the volumes here, but if you start to fit the model, you get quite good strain patterns. So you see a lot of the features that are very well captured by the model. Pre-stretch, rebound stretch in the septal areas, typical aspects you see in LVAV patients. Also, of course, in these baseline models, we see quite a heterogeneous workload, as you would expect in those patients. If you then apply virtual CRT in these digital twins, we see a homogenization of the mechanics, which you would expect. And that's mostly due to resynchronizing the mechanical delay. And the heterogeneity that is left is mostly the non-electrical substrates that you do not really treat with CRT. Well, to do statistics, we sort of had to put this in one number, and we looked at the change in workload, which we knew already from previous and clinical studies, that is very well correlated to outcome after 6 months. Here we see the real response, the reverse remodeling, plotted against the pacing-induced, the virtual pacing-induced work redistribution in those patients. And we get a rather nice correlation. It's not perfect, of course, but there are so many other factors that influence CRT response than just the phenotype of the patient. What is interesting, though, is this is, while labeling the patients, here the red dots are the class 2 indications, and the blue ones are the class 1 indication patients. Recently, the EC guidelines have changed. The LVUB definition has become much stricter, and if you would apply those guidelines to the same data set, you see that actually many of the old, let's say, with the old criteria, class 1 indication patients turned into class 2 indication patients. Whereas these digital twins clearly predict a good response, at least they correlate with that. So this is somehow worrying, and this is how you can see how dysfunctional twinning might be useful if you put it in its clinical context. Okay, I have not much time left, but I'll do this very quickly. Another application is more for monitoring of patients, or actually phenotyping longitudinally, and this is about a very awful disease. It's called arrhythmogenic right ventricular cardiomyopathy, and I say on purposely right ventricular because this is mostly about the PKP2 genetic variant, which is really affecting the RV mostly. Other variants are also biventricular. But the nasty thing here is that the first symptom can be sudden cardiac death, also in young asymptomatic people. And well, we're collaborating with groups in Utrecht and in Oslo, and they have a very good follow-up and family screening program for those patients. So they have their hands on, and we did previous studies as well, where we show that in early stages of disease, you see already mechanical abnormalities that are not visible on ECG even, at least not the criteria and the task force criteria of these patients. So what Nick and Vero, two PhD students at the time, did is they took actually longitudinal echoes, so 313, of 82 early stage ARVC patients. That means those are genopositive subjects that came out of family screening. They have normal ECG, they have normal Holter, they have normal MRI, and we had echoes because those groups are just interested in echoes. So we decided to make digital twins of all these echoes to see if we see an evolving disease over time. And well, this is such an example. We have only RV, well, we have RV strain here. So from apex to base, 3 patterns. The beauty of these patients is they're usually healthy. So they have a very good echocardiographic window. So the quality of those strain patterns is very high, which is often not the case in heart failure patients. And here you see in 3 moments, you see an evolving, clearly evolving disease. Well, Nick also included measurement uncertainty here, so that's why you see these confidence intervals around these signals. And he quantified in all those 313 echo sets, he quantified actually regional contractility from apex to base, and you see a growing heterogeneity over time in this patient, both in contractility, not so clear in compliance, but still a little bit, and not really a change in mechanical activation delay in this particular case. Well, what made this study very important to the clinicians is because we subdivided this group in 3 age groups. So the young ones, middle age, and older ones. And the reason that was done is that the current guidelines actually recommend to stop following up at older age. And our digital twins actually show that the myocardial disease development is actually sort of independent from age. So it happens in older elderly as much and as fast as it does in younger patients. So that's really raising the question, isn't it better to actually keep following those patients during echo or ECG? And that's currently being discussed in that community. So I hope I gave you some impression of how we use our CircAdapt framework for in silico phenotyping and also in silico trialing, if you want to use that word. And well, we do virtual stress testing as well, which is really, I think, something that we should explore more, and also is clinically being done more in the heart failure field. And with that, I would like to end with my conclusions. Well, just in the interest of time, you can read them here. I think it was pretty clear from my presentation, I hope. And please visit our framework there. Nick presents it on his poster. If you're interested, feel free to reach out. This is the team. Of course, many people, also a mix of engineers and MDs in our group, which I think is very important for the work we do, especially in terms of application in the clinic. And I take the opportunity to make a little bit advertisement for this European Heart Journal, sister journal, if you like, because we're super interested in digital twin, applied digital twin studies. Okay, thank you. And Blanca?
I'm going to change question.
Yeah.
So congratulations, Joost. I think you are very close to clinical impact, and that's very impressive. In the studies we have routinely, we have tens of patients, sometimes hundreds of patients, and that's actually very low numbers for clinical impact compared to American hospitals that are doing thousands of patients. So what are your plans of scaling up? In terms of not only, of course, we have the problem of availability of data, but maybe not so much with echo. So what are you thinking in that space?
Well, I'm not thinking too much in those big numbers. I think what I would see feasible is that some of this technology could directly be implemented in an echo machine. I mean, currently, there is a lot of attention to strain patterns. People know it's useful, but the clinicians really don't know how to interpret them, which I can understand because they're super complex and it looks like a spaghetti. So you need a very high training level to be able to translate it to actually substrate recognition and then determine, is that actionable clinically? So I think imaging companies could be interested here to provide a pathological, an interpretation of pathology on a regional basis. Well, that does not really answer your question. What we're currently doing quite a bit is in patients with HFpEF, also doing the same trick. And the beauty there is that it's not so much a heterogeneous problem. You can even do global fitting of constitutive parameters, relaxation and stiffness properties. So it actually makes it very clinically feasible. And there we're collaborating with Dutch consortia with large numbers of HFpEF patients. But yes, you know, the data availability for these kind of fitting thing is a problem because only specialized centers do the 18 segment strain patterns with echo. And that's why I think in, for example, HFpEF patients, you need probably global longitudinal strain pattern, which is fairly available, left atrial strain, and those techniques are really improving the reliability, but still they're noisy. Alistair.
Hi, yeah, very nice. I really like the parsimonious approach and trying to get the most out of the data that you've got. I've been reading some echo literature recently that have been saying, you know, strain isn't great for work. It's really the volume and pressure that you need.
Mm-hmm.
And some of these people are saying that maybe MAPC relates better to work than longitudinal strain. But you're including volume as well, aren't you?
Yes.
So you've got the strain and the volume transients over time, the whole cycle.
Yes. Yeah.
So maybe your models are kind of getting around that issue.
Yeah, what is important for our fits here, and that is often what is missing, which annoys us, but volume you can get. You know, it's a standard measurement. It's maybe unreliable, yes, we know that, and that unreliability is pretty well quantified. But the wall volume around it, that is not so available. And for our work estimates, that is important. You know that in the original, maybe the original one fiber model, it's the ratio of wall volume over cavity volume that actually dominates the stress and thereby also the work. So yeah, I think, well, also the echo community will improve that. I mean, these technologies are really improving rapidly, certainly with AI. So I'm confident for the future. Yeah.
Thank you, and let's speak through again.